Okay, so here is the first free response problem from the rotational dynamics test. All attached. Calculate the linear acceleration of the block. Okay, so this is a kinematic problem. We just know that the block is going to fall with constant acceleration. So this model is a constant acceleration model. It gives us t, gives us delta x. It's released from rest, so that's v naught. This is t, and this is our delta x, which is equal to x minus xo. So we have d equals 0 times t plus 1/2 at squared. So solving for a, because it says we want that linear acceleration, a is equal to 2d over t squared. D and t are measured. What quantity should be graphed to get the acceleration of the block? Okay, well, we just found that a is equal to 2d over t squared. So if we rearrange this, we can see 2d is equal to a times t squared. And this follows a y equals mx plus b format. So if I plot 2d on the y-axis and t squared on the x-axis, I'll get a straight line, and the slope will be equal to the acceleration. Okay, so you can see I've copied over here my data table, squared time multiplied by d by 2, plotted my 4 points. I used a straight line tool on my computer to get a straight line fit. You would use a ruler or any straight edge. And now I'm going to use my graph to calculate magnitude of acceleration, which for my graph just means find the slope. So I'm going to pick 2 points on the line of best fit, not data points. AP specifically looks for that. So then I have this run and this rise. So my rise would be 3.6 meters. And my run would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16. So 1.6 seconds squared. So 3.6 meters over 1.6 seconds squared gives me my acceleration. Which is 2.25 meters per second squared. Whoops. Meters per second squared. Now, when I did this a previous time, I got an acceleration of 2. There is a margin of error that AP accepts around this because they know everybody's going to draw their best fit lines a little bit different. Okay, so now it says calculate the rotational inertia of the pulley in terms of MRA and fundamental constants. So what I know is that the net torque is equal to I times alpha. And with the setup here, I know that the linear acceleration here will be related to the angular acceleration here because the string doesn't slip on the pulley wheel. So A is equal to R times alpha, or alpha is equal to A over R. So if I make the substitution here, the net torque is equal to I times A over capital R is the symbol that I'd have to be using here. A over capital R. And I'm trying to find the rotational inertia, which is this thing, I. So the net torque times R over A is that moment, but net torque is not an allowed symbol, so I have to get a better expression of it. So I have this tension force times this radius, R. T times R is going to be tau net. T is not allowed. I think about the force diagram for my hanging mass, I've got tension up, and I have mg down. And I believe m is the mass. Yep, it's m. So I know for that hanging mass, F net is equal to m times a. So it's accelerating this way. So mg minus t equals ma. So mg minus ma is equal to the tension. Now I can substitute all of this back into here and then this back into there. So the net torque is mg minus ma times r. That's tau net. Now I got to multiply by r. And then I have to divide by a. And this whole thing is equal to the moment of inertia. So if I just group some terms and simplify, I might write this mr squared times g minus a all over a. All right, in this last part of the problem, they've kind of set us up to understand how to answer this. A common mistake would be to say that friction is the cause, but if friction were acting, it would make the moment of inertia that we find experimentally bigger than what we measure. And here, the experimentally determined moment of inertia is smaller. So we need a different explanation besides friction. And this expression here is going to be the key to it. So if you look, it tells us what that moment of inertia depends on. Moment of inertia is equal to mr squared times g minus a all over a. So if the measured I, meaning like we take the pulley off and we set it on a scale and we find its mass and we find its radius, what we get from that is greater than this quantity, mr squared times g minus a over a, which would be our kind of like moment of inertia determined from this experiment. Well, it means that the m that we're using in there is too small. So the m we're using in this expression is too small. The r that we're using is too small. Or the a that we're using is too large. So there's a number of explanations that you can give for this. The two that I think are most reasonable given the experimental setup is the radius that we're using is too small. That could be because in reality that string is wound around many times. So as it winds over itself, the effective radius that we see might be larger. So we might write that the string is wrapped over itself, making the effective radius larger than what was used in calculation. Another reasonable explanation for the acceleration being too large is that the string slipped, and so the acceleration that you measure is actually bigger than what it should have been, resulting in a moment of inertia that is too small from our formula here. So the key thing I see here is they've set you up to use the formula to answer the question, and they do this a lot, so be ready for it.